Okay. So the next lecture is the first lecture out of 4 hours mini course. Speaker is Hugh Woodin, and the title is The HOD Dichotomy, Weak External Models and Universality.
Well, thank you all for attending. I'm giving 4 lectures. I'll be surveying basically inner model theory with the goal of perhaps an ultimate version of L. And so I'm also going to be trying to show how far one can go with relatively simple arguments. Nothing I'm going to do today couldn't have been done 30 years ago when I was a young set theorist. All right. So again, I'm going to be setting the stage today on why an inner model for supercompact would be a very interesting object. And then in the next 3 lectures, I'll be discussing how the current technology, there are obstacles to the current technology. All right, so let me remind you about supercompactness. So if kappa is a regular cardinal and kappa is less than lambda, p kappa lambda is the set of all subsets of lambda of size less than kappa. That. A filter on p kappa lambda, which is really a subset of the power set of p kappa lambda, is fine if for every alpha, the set of set sigma and p kappa lambda such that alphas and sigma is a large set. It's normal if for every function from p kappa lambda into lambda, if on a large set f of sigma is in sigma, then it's constant on a large set. Okay. Okay, so this is the ultrafilter definition of a supercompact cardinal. If kappa is an uncountable regular cardinal, then kappa is a supercompact cardinal. If for every lambda, there's an ultrafilter U on p kappa lambda, such that U is kappa complete and U is normal and fine. And there's a natural equivalence in terms of elementary embeddings. The elementary embedding version was given earlier. So if kappa is an uncountable regular cardinal, the following are equivalent. It's a supercompact cardinal, or for every lambda bigger than kappa, there's an elementary embedding from V into M such that the critical point, the first ordinal moved, is kappa. J of kappa is bigger than lambda, and M is closed under lambda sequences. It does not really need any formal notion of classes because you can restrict to sigma 2 definable classes, both J and M. And I'm going to assume you're more or less familiar with the proof. You just take the ultrapower. If this is true, then the pointwise image of lambda is an M, and then you can use that to define an ultrafilter using J. If it's supercompact, you take the ultrafilter on p kappa lambda, you take the ultrapower, it's well-founded because it's countably complete, and the identity function represents J image lambda, and that will give you closure under lambda sequences. Okay, I want to recall solid-based lemma, which is a remarkable lemma, and in some sense it's a precursor to much of what I will be talking about today. But I want to give you a specific proof of the lemma, because we'll need that later in the week. So suppose kappa less than lambda are regular cardinals, and we have a well-ordering on H lambda plus. Then there's a set in p kappa lambda such that the following hold. First, if U is a kappa complete normal fine ultrafilter on p kappa lambda, then this set is of measure 1. Well, that's not so interesting because I could just take the whole set. But here's the remarkable fact. If sigma and tau are in X and their soups agree, then they agree. So the soup function's 1-to-1 on this set. And then the third is that X is uniformly definable in H lambda plus and less than. Doesn't depend upon the ultrafilter. And that's the uniformity that we're going to need. So this is a remarkable fact. It says that in this situation where lambda is regular, there is a set of measure 1 for the supercompactness measure on which the soup functions 1 to 1, and that set does not depend upon the choice of the ultrafilter. And at the time, this was cited as strong evidence for being able to do an intermodal theory, because it says that the supercompactness ultrafilter is really equivalent to an ultrafilter on lambda. So you could construct from it, but that doesn't work. Okay, so here's the proof. Let S be the set of alpha less than lambda, such that the cofinality of alpha is omega. And now split S into lambda many stationary sets. Okay, you can show that. Okay? Now let X be the set of all sigma in p kappa lambda, such that the cofinality of the sup of sigma is less than kappa. Sigma is the set of all alpha less than sup sigma, such that S alpha intersect C is non-empty for all closed cofinal subsets of sup sigma. And then it's not so hard to check that X witnesses a lemma. So you get the canonical set just by splitting the cofomega points into lambda many stationary sets and then defining your set. All right, so if you're going to build an inner model with a large cardinal, it's natural to, you don't want to talk about arbitrary classes. That turns out to be too weak a notion. So we would like the inner model of the large cardinal to have that large cardinal there because it exists in V. And the prototypical example would be Kunin's construction of the inner model for a measurable cardinal, L mu. So you just take the measure, the normal measure at kappa, witnessing that kappa is measurable, you construct from that normal measure, and that gives you a nice inner model. Okay, but abstractly, that's a transitive class with a measurable cardinal. And the measurable cardinal is a measurable cardinal because there's a measure in V whose intersection with the model is in the model. So we're just going to do exactly that. So a transitive class inner model of ZFC is a weak extender model for delta is supercompact, it should have said. If and only if for every gamma bigger than delta, there's a delta complete normal fine measure mu on p delta gamma, such that two things happen. First, n intersect p delta gamma is a set of measure 1, so it's in U, and that U intersect n is in n. If you drop the first condition, then L would be a weak extender model, right? Because if the inner model doesn't have a set of measure 1, then the intersection of the ultrafilter with the model is not so interesting. All right. So, okay, so the idea now is however we envision the inner model that we're looking for supercompact, it should have this property. And the idea here is this inner model has a supercompact that's related to a supercompact in V. And the question then becomes, can we analyze n and deduce anything interesting about n in order to give us clues of how to find the model we're really interested in, which is a generalization of L, or maybe we can prove that such a model n is too pathological and therefore rule out the existence or the extension of the inner model program to the level of supercompact. All right, so if we have a transitive class and delta is a regular cardinal, we could say that n has a delta covering property if for every subset of n of cardinality less, oh, there's a missing, all these misprints. Oh well, must be the wrong version. For all sigma contained in n such that the cardinality of sigma is less than delta, it's covered by a set in n of cardinality less than delta. So if n is a weak extender model for delta supercompact, then it has the delta covering property. What's the proof? Take a subset of n of size less than delta. Since n is a model of ZFC, we can reduce to the case that sigma is a set of ordinals. Let lambda be bigger than delta, be such that sigma is a subset of lambda. Let U be a delta complete normal fine ultrafilter on p delta lambda, such that n intersect p delta lambdas in U. That exists because n is a weak extender model for delta supercompact. Now U is fine and delta complete, so the set of tau and p delta lambda such that sigma is contained in tau must be a set of measure 1, and so there must be a set in that set of measure 1 in N, and that's our covering set. A trivial argument. All right, but now let's get an easy consequence of this, which is more interesting. So suppose N is a weak extender model for delta supercompact. Gamma bigger than delta is a regular cardinal in N. We're not assuming it's a regular cardinal in V. Then the V true cofinality of gamma is equal to the true cardinality of gamma. Okay, well, let U be a delta complete normal fine ultrafilter on p delta gamma such that N intersect p delta gamma is a large set and U intersect N is an N. We have these for all lambda, so we have them for all ordinals. By Solovey's lemma applied within N, remember gamma is a regular cardinal in N, there exists a set X in N intersect U such that the sup function is 1-to-1 on X, the function pi. Well, let C contained in gamma be a closed cofinal subset of gamma of order type the true cofinality of V. C is chosen in V. Let J from V into M to be the ultrapower embedding given by U. Then J image gamma has the unique is the unique element of J of X such that sup sigma is sup J image sigma, because the sup function is 1-to-1 on X. But C is closed and cofinal in gamma, so sup J image gamma has to be in J of C. Well, that tells us that the set of sigma and X such that sup sigma is in C is in U, because J image gamma is in J of that set. Finally, since U is fine, the union of sigma and X such that sup sigma is in sigma is gamma, and therefore the true cardinality of gamma is the cardinality of V of C, that's the cofinality, times delta, so that's just the true cofinality of gamma times gamma. That's the theorem. All right, so just let's go back. We just proved that if gamma is a regular cardinal in N, bigger than delta, then the true cofinality of gamma is the true cofinality of gamma. All right. Now this has a remarkable consequence. Suppose N is a weak extender model for delta supercompact and gamma bigger than delta is a singular cardinal. Then gamma must be a singular cardinal in N, and the successor of gamma computed in N must be the true successor. So we're getting rather remarkable closeness of N to V. Well, let's look at the proof. If gamma is a regular cardinal in N, then by the lemma we just proved, the true cofinality of gamma is equal to the cardinality of gamma. And that contradicts that gamma is singular. Right? Remember, gamma is a singular cardinal in V. We're trying to show that it's singular in N. Where if it were regular in N, we would infer that the cofinality of gamma is the cardinality of gamma, but gamma is singular. Okay, so that proves that gamma is a singular cardinal in N. Now let's switch attention to gamma plus. Well, let's let lambda be the gamma plus of N. Certainly a regular cardinal in N. So, by our lemma, the true cofinality of lambda is the true cardinality of lambda. But the cardinality of lambda is bigger than or equal to gamma. And cof gamma is a regular cardinal. So the cofinality of lambda has to be bigger than gamma. And the only way that can happen is if lambda is gamma plus. That's it. Okay, so now we're getting more information about how close this mythical model must be to V. Maybe we're getting too much information. All right, so now I want to recall Magador's reformulation of supercompact, which is useful for what we will do. First, let me recall what the definition of an extendable cardinal is. If delta is a cardinal, delta is extendable if for every lambda bigger than delta, there's an elementary embedding from v lambda plus 1 to v pi of lambda plus 1, such that the critical point of pi is delta, and pi of delta is bigger than lambda. So it takes v lambda plus 1 and elementarily embeds it into an extension. Critical point is delta, and we require that pi of delta is bigger than lambda. You don't actually have to require the pi of delta bigger than lambda in ZFC, because you can infer that there must be such an embedding where pi of delta is bigger than lambda if it were not. But in ZF, it's a very different notion. Okay, so then Magator proved an equivalence to supercompact, which feels a little bit like extendibility. So he showed the following are equivalent. Delta is supercompact, and the second, for every lambda bigger than delta, there are delta bar, lambda bar less than delta, and an elementary embedding from v lambda bar plus 1 to v lambda plus 1, such that the critical point of pi is delta bar, and such that pi of delta bar is delta. So an extendable cardinal is shifting up. In this reformulation, you're shifting from below, and the critical point's coming up to delta. Okay, and then, so I'm not proving this, I'll prove a stronger version. Then there's the weak extender model version of Magator's lemma. So it's exactly the same. So we have a weak extender model for delta supercompact. I'm just going to give you the conclusion. Then for every lambda bigger than delta, and for every a in v lambda, there exists delta bar less than lambda bar less than delta, and a bar and v lambda bar, so we're shifting down, and an elementary embedding from v lambda bar plus 1 to v lambda plus 1. Everything was like it was before, except we're going to require that pi of n intersect v lambda bar is n intersect v lambda, another misprint. Goodness. Lots of corrections. And pi of, now this is the key thing, 3, the restriction of pi to n intersect v lambda is actually in n. So it's exactly like Magator. You can shift from below, except you're moving n correctly, and n sees the embedding. Okay, so I'll give you the proof, and from this proof you can figure out the proof of Magator's lemma. All right, by increasing lambda and replacing a by the pair a lambda if necessary, we can reduce to the case that lambda is the cardinality of v lambda. That just simplifies things. And that the cofinality of lambda is omega. Now, since lambda is a cardinality of v lambda, that must be true in n. So in so n intersect v lambda has n cardinality lambda. Let's fix a bijection between lambda and n intersect v lambda, call it rho, such that rho is in n. Remember, weak extender model only gives us measures on p delta of lambda, and I want a measure on n intersect v lambda, p delta of n intersect v lambda. So I'm going to use rho to move that around. Let U be a delta complete normal fine ultrafilter on p delta of lambda such that n intersect p delta of lambda is in U and U intersect n is in n. I guess I should have said at the beginning, I'm going to be covering a lot of material. I'll make the slides will be available. And in an uncharacteristically efficient fashion, at least for me, I actually have 80 pages of notes, which I will make available at some point. Nicely tacked and hopefully without as many misprints. Okay, so we get this measure. Now for each sigma in p delta of lambda, we can take the image of sigma under our bijection. We'll call that x sigma. So that's going to be now a subset of n intersect v lambda, or n lambda if you prefer. Now let Z be the set of all sigma in p delta of lambda such that x sigma is an elementary substructure of n intersect v lambda. I'm now running about 2 misprints a slide. I'm going to have to do some work tonight. Thus, by the normality and fineness of U, Z is in U. Okay, we have a bijection between lambda and n intersect v lambda. We have a normal fine measure on p delta of lambda. So for almost all sigma, when we move over under the bijection, we get an elementary substructure. For each sigma, let m sigma be the transitive collapse of x sigma. And here's the key claim. Look at the collection of sigma and z, that's where we had an elementary substructure, such that m sigma, the transitive collapse of x sigma, is just the rank initial segment of n, given by the order type of sigma. The claim is that's in U. Okay, now you can verify this easily by just working in n and doing the ultrapower analysis. Okay, if you did it in V, you'd have this normal fine measure on p kappa lambda, bijection between lambda and v lambda. For every sigma, you'd have an x sigma containing v lambda. You'd want to show that for almost all sigma, x sigma transitively collapses to a v alpha. We just take the ultrapower, and J image v lambda transitively collapses v lambda, which is an initial segment, rank initial segment of the ultrapower. That proof doesn't quite work if you tried it in V, because you don't know what's happening with n versus j of n. So you work inside n. And then it must be true, because you just work that proof in n. So for a measure one worth for a U measure one worth of sigma, when we pass to the elementary substructure of n intersect v lambda and transitively collapse, we get a rank initial segment of n. Okay, so now we do the ultrapower in V by U. We have that the cardinality of V lambda is lambda and the cofinality of lambda is equal to omega. So not only is mu closed under lambda sequences, it's closed under the power of lambda sequences. Okay? And so J restricted to V lambda plus 1 is in mu. Mu sees the embedding from V lambda plus 1 into itself, and that's an elementary embedding. Further, by claim 1, the claim we just proved, Ju of n intersect V lambda is n intersect V lambda. So you put everything together, and what you get is that Ju restricted to n intersect V lambda is in Ju of n. You get that the cofinality of lambda and n is less than delta. You get Ju restricted to n intersect V lambda plus 1 is in Ju of n. And then finally, you get that Ju of n intersect V lambda is n intersect V lambda. And 1 through 4 imply that the conclusion of the lemma holds for Ju of a, Ju of lambda, and mu for Ju of n. So we've just taken the ultrapower and verified things are working on the J side. So the conclusion of the lemma holds in V for A and lambda relative to N. It's a very common technique. You're trying to show something. You show something in the ultrapower and then infer it in V. All right, so the short of it is, and all you have to remember, is we have the N version of Magador's lemma holding if N is a weak extender model. All right, so now we're going to get a really remarkable closure condition. We're going to prove that if, well, let's state it. Suppose N is a weak extender model for delta supercompact and that gamma bigger than delta is a cardinal of N. Suppose that we have an elementary embedding from H gamma plus as computed in N to Hj of lambda plus, again, as computed in N. So remember, H kappa is a set of all sets of hereditary cardinality less than kappa. Gamma is only assumed to be a cardinal of N here. Okay, suppose this elementary embedding has critical point greater than or equal to delta, then it's in N. This is a remarkable closure property. It's saying embeddings of N with critical point bigger than delta, these are embeddings in V, are actually in N. All right, so what's the proof? Well, we fix a lambda bigger than J of gamma, such that, again, our favorite assumption, lambda is a cardinality of V lambda. And now we're going to be using Magador's reformulation. We set A equal to J. So by the Magador reformulation, or by the Magador reformulation in the sense of weak extender models, we get that they're delta bar less than lambda bar less than delta and A bar in V lambda bar. We're downward reflecting. We're pushing up from below an elementary embedding from V lambda bar plus 1 to V lambda plus 1. And we have these properties. The critical point is delta bar. It's sent up to delta. We've reflected A, which is our J, into an A bar. Pi of n intersect v lambda bar is n intersect at least I'm consistent with my typos. That should have been n intersect v lambda. I'll correct all of these. And then that pi restricted to n intersect v lambda bar is in n. So we have our objects upstairs. We're finding images below. We have an embedding pushing up. It's moving that bit of n up to the bit of n, and n sees the restriction of the embedding to n. Okay, so we could then call A bar a J bar, and because A bar has to have all the properties that A has, and A is J, our elementary embedding, so J bar is going to be an elementary embedding from some H gamma bar plus of n to some H J bar of gamma plus n. So we've reflected our J down below. What we're going to do is show that J bar is an n. Well, since pi of J bar is J, and since pi restricted to n intersect v lambda bar is an n, that will tell us that J is an n. So we're going to reflect down, show that the reflected object is in n, and then use the fact that n sees this embedding to infer that J is in n. All we have to do is show that J bar is in n. Okay, so we need to code up J bar. Here's how we're going to do it. We'll let E be the set of all pairs A psi. A is in the power set of gamma bar intersect n. Psi is an ordinal less than J bar of gamma bar, and psi is in J bar of A. This codes up J bar. We're going to prove that E is in n, and this implies that J bar restricted to the power set of gamma bar intersect n is in n, and that implies J bar is in n because J bar acts on H gamma bar plus. So everything in H gamma bar plus is coded by a subset of gamma bar. All right, so here's the key claim that pi bar restricted to H lambda gamma bar plus of n is in H gamma plus of n. It's a small set. This is because pi restricted to n intersect v lambda bar is in n, noting that H gamma plus in the sense of n is closed under gamma sequences in n. All right, so now we're going to let pi star be pi restricted to H gamma bar plus of n, and we just noted that's in H gamma plus of n. So pi star is in the domain of J. J acts on H gamma plus of n. So now we get this following equation. We fix an A in P of gamma bar intersect n, and our ordinal less than J bar of gamma bar. We're trying to show n needs to be able to figure out when psi is in J bar of A. Well, psi is in J bar of A if and only if pi of psi is in pi of J bar of pi of A. We're just applying pi. That's if and only if pi of psi is in J of pi of A. Okay, and that's if and only if pi of psi is in J of pi star of A, because pi and pi star agree on the subsets of gamma. And now we're going to move the J in. And that's if and only if pi of psi is in J of pi star of J of A. See, it didn't make sense to apply J to pi because pi is not in the domain of J. But pi star is in the domain of J. And pi star are in agreement where we're interested. So we can move J in. And so that's J of pi star of J of A. But A is fixed by J. Okay, A is a subset of gamma bar, which is less than delta. So that's J of pi star of A. Okay, so we've computed, we're trying to answer this question, given A and psi, and we've reduced it to this. Pi of psi is in this. But pi star is in n, j of pi star is in n, and so we have everything we need to compute it. Okay? We have pi restricted to j bar gamma bar. We know how to, and so we have j of pi star. Both these functions are in n, so E is in n. Okay, so it's just a simple trick. Okay, so that proves j bar is in n, pi of j bar is j, and so j is in n, and that's what we wanted to prove. All right, so we've got a remarkable closure property for the weak extended models. Remember, we're trying to get as much information about these models as we can, because the L-like model, if it exists, is going to have all of these properties. So we have Kunin's theorem. Suppose lambda is a cardinal, then there's no non-trivial elementary embedding j from v lambda plus 2 to v lambda plus 2. And I'll give you a quick proof of it. Let j be given. Know that v lambda plus 2 is logically equivalent to h cardinality of v lambda plus plus. So cardinality of v lambda, we can reduce the case as lambda. So j yields certainly an elementary embedding from h lambda plus plus to h lambda plus plus. Necessarily pi of lambda is lambda, and pi of lambda plus is lambda plus. Actually, I don't need to know that cardinality of v lambda is lambda here. So j will certainly give that embedding pi. We're going to do the same argument over and over again. We split let S be the points, the ordinals less than lambda plus of cofinality omega, and we partition it into lambda plus many stationary sets. We let T alpha, alpha less than lambda plus be pi of the sequence. The sequence has length lambda plus, and pi of lambda plus is lambda plus, so pi of the sequence has length lambda plus. And we'll let C be the points in S such that pi of alpha is S. Note that pi of S is S. C is omega closed and cofinal in S. An omega limit of fixed points is a fixed point. By the elementarity of pi, and since pi of S is S, for each alpha less than lambda plus, T alpha is a stationary subset of S, because every S alpha was a stationary subset of S. And so for each alpha less than lambda plus, C intersect T alpha is non-empty. We'll let kappa be the critical point of pi and choose a point there. So we have a fixed point of pi that's in T kappa. Choose beta less than lambda plus, its size in S beta. S beta was a partition of S. So this ordinal psi that we chose in C intersect T kappa has to be in one of the S alphas. But then psi is equal to pi of psi as an element of pi of S beta, which must be T pi of beta. But that implies pi of beta is kappa. Psi was in T kappa, and the T alpha are pairwise disjoint. But that contradicts that kappa is the critical point of pi. Okay, so there's several proofs of Kunin's theorem. This is a different proof than Kunin's original proof. It uses actually a little bit less choice, and in certain situations it gives you positive information instead of 0 equals 1. Okay, so we get a corollary. Let M be a weak extender model for delta supercompact, then there's no non-trivial elementary embedding J from n to n such that delta is less than or equal to the critical point of J. We get a rigidity. Well, by the remarkable closure condition, for each kappa bigger than delta, J restricted to n intersect v kappa plus 1 is in n, because J goes from n to n. Thus, J is amenable to n, and in particular, there exists a cardinal lambda of n such that the crit J is less than lambda, J of lambda is lambda, and such that J restricted to v lambda plus 2 intersect n is in n, and that contradicts Kunin's theorem. Okay? Okay, so we're getting more and more information. All right, suppose we have two transitive models of ZFC minus power set and an elementary embedding between them. Then it's cofinal if the range model is a union of the elements of the domain. Or if you want, since if these are ZFC models, it would be the ordinals, or cofinal would suffice. So this in the ZFC case, you would just say pi image of the ordinals is cofinal in the ordinals. That doesn't work in ZFC minus power set. We don't have the rank function. All right, so suppose we have two transitive models of ZFC minus power set and a cofinal embedding between them. We let kappa be the critical point of pi, and we choose eta and n. Then for each a finite subset of eta, we can get an ultrafilter. E sub a is a set of a and n such that a is in pi of big A. It's hard to talk in fonts. And let E be that sequence. So it's a directed family of ultrafilters indexed by the finite subsets of eta, and that's the kappa eta extender over n, which you'll be hearing a lot about. So I've just defined extender. Suppose that M is a transitive model of ZFC and that E is an M extender, in other words, comes from a cofinal embedding, we can form an ultrapower. We take and define the ultrapower of M by E to be the direct limit of all the ultrapowers of M by the E sub A for various A. And there's a directed system there on the finite set, and there's a way of fitting together the ultrapowers. Suppose M is a transitive model of ZFC minus power set, and we have an M extender, then the ultrapower is well-founded. If M sub B is a transitive collapse of the ultrapower, we get an elementary embedding from M to ME. Then pi sub B is an elementary embedding. The critical point of pi E is less than eta, less than the ordinals of ME. And if F is the kappa eta extender given by pi E, then F is equal to E. So an extenders come from an embedding. And the embeddings and the extender can be used to build an embedding from which you can get back the extender, just like ultrafilters. Okay, so here's a variation of the universality theorem. I'm not going to prove it, the closure property. If n is a weak extender model for delta supercompact and E is an end extender of length eta with critical point of E greater than or equal to delta, and if you take the ultrapower embedding, suppose that for every subset of eta, pi E of A intersect eta is in n. That's the closure property. That's saying n is somehow closed under the extender. Then the extender is in n. E intersect n is in n. So if you have an extender, if you have an n extender, it doesn't have to be a V extender with critical point greater than or equal to delta. And when you take the ultrapower of n by that extender, if sets are being sent to sets in n in this restricted sense, then the extender intersect n is in n. It's the same proof as the closure under embeddings. Now, this is not, in general, a very strong closure condition. Suppose, E intersect n in n is a strong closure condition, but you might suspect that this is where something funny is happening. But notice that if E is an L extender, and you take the ultrapower of L by E, then that's got to be L. And so pi E of A is in L for all A. So requiring that pi E of A is in n for A and n is not a terribly restrictive condition. That's not where the magic is happening. All right, E, we'll simply say E is an extender if it's a V extender. And I now realize I have hopelessly overestimated things. So this may actually become a two-part lecture, in which case I don't know what's going to happen later on. We'll say an extender is lambda complete, an extender of length eta, if eta to the lambda is included in M, where M is the ultrapower of V by E. Okay, so suppose you have a kappa eta extender, and P is in B kappa, and G is a generic set. So the size of the partial order is less than the critical point. Then E naturally defines a kappa eta extender in V of G, another typo. And JE as computed in V of G restricted to V is just JE. You have an extender, do small forcing, the extender naturally generates an extender, And the new embedding is just an extension of the old embedding. So there's a technical lemma, and in the interest of time, I guess, and after all, I'm giving you these wonderful set of notes, I'm going to skip the proof. It is a very useful lemma, and I'll show you why. So let me just read the statement. We have delta less than kappa, and E is an extender which is delta complete with critical point kappa. Okay, so we have delta and we have kappa. And we have an elementary embedding now from V into M, but this can be in a generic extension. So it's a generic elementary embedding such that M is J of F of alpha for alpha less than delta. Okay, so everything in the ultrapower is generated by moving functions and applying them to things less than delta, which if you remember is less than the critical point of E. G is V generic for some partial order of size less than delta. And now here's the conclusion. Take J of E as computed in V of G. Remember, E generates an extender in V of G, small forcing below the critical point. But look at that embedding's action on M. That's M's embedding for J of E. So E and J of E are somehow the same, doing the same thing as far as generating elementary embeddings as far as M is concerned. Of course, E is not in M. That's the point here. All right, so I'm going to make you read the proof because I'm going to run out of time. Sorry, I hate it when people do this. But you can see it was a really nice proof, no misprints at all. Okay, so here's the corollary we want. And I'm stating it in a generic version because when you have small, large cardinals, like Woodin cardinals, you get many generic embeddings. Okay, so this is a way of generating all kinds of weak extender models. Okay, so we have delta less than kappa, kappa supercompact. We have our generic elementary embedding, J from V into M. M is generated by ordinals less than delta by applying taking J of functions in V. G is V generic for some partial order of size less than delta. Then in V of G, M is a weak extender model for kappa supercompact. So we have a supercompact, kappa. We have some generic embedding generated below delta, and we're just taking the generic ultrapower of V. Then kappa is still supercompact, small forcing preserved supercompact. What's remarkable is that the image of V, the generic ultrapower of V, is a weak extender model for kappa supercompact in the extension. And that follows from, what? Or I just want less than kappa, actually. Kappa's big, yeah. I just put, yeah, this cardinality P less than kappa is what is sufficient, but this is certainly okay. I'm actually going to use this in the case where P is trivial, in other words, not a generic embedding. I'm not going to make you sit through the proof, it just uses that previous lemma, and I didn't show you that proof anyway. Okay, so here's the application, which shows that something interesting is happening with weak extender models. Suppose delta is supercompact, and that another typo, and that N is a weak extender model for delta supercompact. Oh, sorry, no, this is not a typo. Jet lag. Suppose delta is supercompact, then there is, call it N, a weak extender model for delta supercompact, and a non-trivial embedding from N to N with critical point less than delta. Remember, we showed there can't be any such embedding with critical point bigger than delta, yet there can be one with critical point less than delta. This also shows that you might, before this, start to think a weak extender model is too strong a notion. It's implying that N is too close to V. Well, this is saying N's not too close to V because V can have an elementary embedding from N to N. All right, so let kappa less than delta be a measurable cardinal. Let U be a kappa complete normal ultrafilter on kappa. We'll do the iterated ultrapower of length omega. So you just M0 U0 is VU, Mn plus 1 is the ultrapower of Mn by Un, Jnn plus 1 is the associated embedding, and then Un plus 1 is Jnn plus 1 of Un. So we're just doing the iterated ultrapower. And then we take the direct limit, that's M omega. It's well-founded. And let's just let N be M omega. Well, and then we have an associated embedding, J0 omega from V into N. Let eta be J0 omega of kappa. Then eta is less than 2 to the kappa plus is less than delta. We have an extender, and N is the ultrapower of V by E. Well, we're exactly in the situation of the lemma, except it's not a generic embedding. I didn't say it had to be a non-trivial partial order. So N's a weak extender model for delta supercompact. The forcing's trivial, so V of G is G. And so we have, so the omega iterative V by any measure below the supercompact is a weak extender model for that supercompact. But J01 of N is N. The ultrapower embedding fixes the omega iterate, and so yields an elementary embedding from N to N. And you can do even more if you throw in the critical sequence. It's still a weak extender model because that's the Precree extension, and that's closed under omega sequences. Okay. Okay, now I thought I'd be about 25 minutes in at this point. I see I have 12 minutes left, so we'll see how this goes. Okay, so the HOD dichotomy theorem, which is the third theorem I wanted to talk about. It's a theorem with a very easy proof with a lot of consequences and raises a very interesting question. So recall Jensen's covering theorem, which I'm going to state in a particular form without mentioning zero sharp. So Jensen's theorem is that exactly one of the following holds. L is correct about singular cardinals and computes their successors correctly. In other words, every singular cardinal is singular in L, and the successor of that cardinal is correctly computed in L. And every uncountable cardinal, so that's option 1. Option 2 is every uncountable cardinal is inaccessible in L. So these are very different behaviors. Either L is very close to V or L is very far from V. I'm going to be trying to sketch a proof of an analogous theorem. May not get through it today, and that's the HOD dichotomy theorem. This is a weaker version than the theorem I'm actually going to prove. Suppose delta is an extendable cardinal, then exactly one of the following hold. Every singular cardinal gamma bigger than delta is singular in HOD, and HOD correctly computes its successor. That's like option 1 here. Or every regular cardinal greater than delta is a measurable cardinal in HOD. So that's actually a bit stronger than here. So it's the same theorem. If you have an extendable cardinal, either HOD is very close to V or it's very far from V. There's no middle ground. The difference between this theorem and Jensen's theorem is that HOD's not canonical. Right? You can force V is equal to HOD. But whatever your situation is, whatever V you're in, HOD must either be very close to V or very far from V if you have an extendable cardinal. All right, so 10 minutes. We'll see how this goes. I have to introduce an intermediate notion. Suppose lambda is an uncountable regular cardinal, then lambda is omega strongly measurable in HOD if there exists kappa less than lambda such that 2 to the kappa in HOD is less than lambda, and there's no partition of the coph-omega points below lambda into kappa many sets, into kappa many stationary sets, stationary in V, such that the partition is in HOD. Okay? Well, let me state a lemma and not insult you with a proof. because I'm running out of time. Let lambda be an uncountable regular cardinal and F be a lambda complete filter on lambda uniform. Look at the Boolean algebra P of lambda mod I, where I is the dual ideal to F. Suppose that B is gamma CC for some gamma such that 2 to the gamma is less than lambda, then the cardinality of B is less than or equal to 2 to the gamma, and B is atomic. Okay? And it's a simple proof. There it is. You'll get it in the notes if you need it. Shouldn't have taken that many slides anyway. Okay, so the point of that lemma, suppose lambda, another misprint, assume lambda is omega strongly measurable in HOD, then HOD thinks lambda is a measurable cardinal. Well, let S be the cofomega points. Let F be the set of subsets of kappa intersect HOD such that S take away A is not stationary in V. F is a lambda complete filter in HOD. Okay, it's in HOD because I just defined it, and it's a lambda complete filter in HOD. Since lambda is omega strongly measurable in HOD, there is a gamma less than kappa such that 2 to the kappa is less, more misprints. I'm going to have to go through my slides tomorrow. 2 to the gamma is, that should have been lambda, and P of lambda mod I is gamma CC, where I is the ideal dual to F, but then that ideal is atomic. I mean, the Boolean algebra is atomic. So the rough, let me give you the short version. If lambda is omega strongly measurable in HOD and you look at the cofomega points, there's a stationary set there that's in HOD that can't be partitioned into stationary sets in HOD. So the club filter on that stationary set, which HOD sees, is an ultrafilter. So you get that lambda is measurable in HOD in a very simple way. It's just the club filter of V on a stationary set that HOD sees. Moreover, the cofomega points can be partitioned into a small number of such sets. It's a really remarkable property. Okay. Oh, sorry. Okay, so now this is going to be the first connection. Suppose delta is an extendable cardinal, then the following are equivalent. One is HOD is a weak extender model for delta supercompact. Remember, that has all the remarkable corollaries. Or two, there exists a regular cardinal lambda bigger than delta, which is, these are equivalent. There exists a regular cardinal lambda bigger than delta, which is not omega strongly measurable in HOD. Omega strongly measurable in HOD look like a very unlikely property. If you have one of those above delta, then HOD must be a weak extender model for delta supercompact. So remember, that implies that it computes all successors of singulars correctly. And those cannot be weakly omega strongly measurable in HOD because they can't be measurable in HOD. So 1 implies 2 is trivial. The point is to get 2 implies 1. And I just did, that's 1 implies 2. I think in the interest of finishing, another proof I'm not going to let you see, but I'll let you scroll through it briefly so you see it's not too bad. And it's in the notes. I apologize for this, but I'm going to have to rethink my next 3 lectures. All right, so here's the HOD dichotomy theorem. Suppose delta is an extendable cardinal, then one of the following holds. Every regular cardinal above delta is omega strongly measurable in HOD, or no regular cardinal is omega strongly measurable in HOD above delta. So that's a much stronger dichotomy. And because I want to finish and get to some more things, I'm not letting you see much, but it's all in the notes. Now, well, maybe I can do this proof since I'm near the end. Okay, so suppose toward a contradiction we have kappa less than gamma are regular cardinals above delta, and kappa is not omega strongly measurable in HOD, and that gamma is omega strongly measurable in HOD. Okay, so the smaller one is not and the bigger one is. Okay, so now we know there's a stationary set in coph omega. The stationary set is in HOD, and the club filter on that stationary set is an HOD ultrafilter. So we have a stationary set in HOD and coph omega that can't be split into truly stationary sets. Okay, let U be, this ultrafilter's in HOD. U is a gamma-complete, normal, uniform ultrafilter on gamma, and S is in U. It's that S that's stationary in coph omega and can't be split. HOD is a weak extender model for delta supercompact because we have one cardinal above delta, which is not omega strongly measurable in HOD. That was kappa, the smaller of the two. Therefore, by the covering property, for each psi and S, HOD cofinality of S is less than delta. We have the covering property. It's a weak extender model. But then the set of ordinals less than HOD, gamma, such that the HOD cofinality of that ordinal is less than psi, is in U. So we have a normal ultrafilter. We have a normal gamma-complete ultrafilter concentrating on singular cardinals. And that's a contradiction. So that proves the theorem. In fact, we actually have the cofinalities less than delta. We could get the contradiction more easily. Now, okay, so that proves the stronger version of the dichotomy theorem, that above an extendable cardinal, either every regular cardinal is omega strongly measurable or none of them are. And this has an interesting corollary. So far everything's been A or B. HOD is close to V or far from V. But there's a very amusing corollary. Suppose that there's an extendable cardinal. Then there is a measurable cardinal in HOD. No dichotomy here. Well, that's kind of a weird theorem. Proves trivial. Well, let delta be extendable. We can reduce to the case that there is a regular cardinal above delta which is not omega strongly measurable in HOD, because if they all are, we've got measurable cardinals. But then HOD is a weak extender model for delta supercompact, so there's a supercompact cardinal in HOD. So either way, there's a measurable cardinal in HOD. And if you manage your resources a bit more efficiently, you can actually prove if there's an elementary embedding from V kappa plus omega to Vj of kappa plus omega with critical point kappa, then there's a measurable cardinal in HOD. You can just use a little bit of supercompactness. Okay, so because I skipped all the proofs, we had to finish on time. So I want to talk about the HOD hypothesis and the HOD conjecture. This is not consistent with the literature because I'm trying to clarify an issue. So the HOD hypothesis is that there's a proper class of regular cardinals which are not omega strongly measurable in HOD. So that's a hypothesis for V. Has a lot of consequences if there's an extendable. It's not known if there can exist 4 regular cardinals which are omega strongly measurable in HOD. It's not known if the successor of a singular strong limit of uncountable cofinality can ever be omega strongly measurable in HOD. And the HOD hypothesis is just saying there are a proper class of cardinals which are not omega strongly measurable in HOD. So to get the consistency of the HOD hypothesis, you have to make every regular cardinal omega strongly measurable in HOD, and we don't know how to do more than 4, and we can't do successors of singular strong limits of uncountable cofinality. So if you assume the HOD hypothesis and that delta is an extendable cardinal, then HOD is a weak extender model for delta supercompact. And then we have the closure condition. Assume the HOD hypothesis, assume there is an extendable cardinal. I'm going to skip all this. Sorry. In the notes, I don't have time. It's about when you might have elementary embeddings from HOD to HOD. All right. Sorry. I'm going to adjust my slides. All right. 1 minute left. Here's the HOD conjecture. That the theory ZFC plus there is a supercompact cardinal proves the HOD hypothesis. In which case, the HOD dichotomy theorem is not a dichotomy. in the context of a supercompact cardinal. It actually just is HOD is close to V. So the analogy with Jensen's theorem breaks. And it has some remarkable corollaries in ZF. Assume the HOD conjecture. That's a number theoretic statement. Assume in ZF that delta is an extendable cardinal. That's the same definition. Then there's a transitive class M inside V. M is a model of ZFC. M is sigma 2 definable from some set in V delta. That's not so interesting. Every set of ordinals is less than delta generic over M, and M thinks delta is an extendable cardinal. So if the HOD hypothesis is HOD conjecture is true, in ZF, if you have an extendable cardinal, there's an inner model of choice that's very close to V. Computes all cardinals correctly above the extendable. So assume the HOD conjecture, suppose delta is an extendable cardinal, then for all lambda bigger than delta, there's no non-trivial elementary embedding from V lambda plus 2 to V lambda plus 2. You get Kunin's theorem in ZF, but you need the extendable. And that's an open question whether there can be a J from V into V in ZF. And this would say no if you have an extendable cardinal. And this motivates what I call the axiom of choice conjecture. Suppose that delta is an extendable cardinal and you collapse V delta to omega, then the axiom of choice holds. And if there's a theorem, if you assume the HOD conjecture and that delta is an extendable cardinal, and you move to, this is in ZF, and you move into L of the power of the ordinals, then delta is still extendable and the axiom of choice conjecture holds. Okay, so if the HOD, so there's this intriguing possibility, if one could prove the HOD conjecture, or verify the HOD conjecture, that if you have an extendable cardinal in ZF, you almost prove the axiom of choice. And that's very counter to the intuition on the connection between large cardinals and the axiom of choice. So everything that I raced over will be in the notes, and I apologize for doing that, and I will shorten my remaining slides, and I will correct the 20,000 misprints that emerged in these slides. So I'll have to stay up all night. So thank you. I'm sorry I went a little over.
Any questions or comments? So what is the L of our set of coordinates?
Just take the smallest inner model of ZF containing all sets of ordinals.
Okay, this is because you don't have choice. Right?
Yeah. Well, right.
Okay.
Yeah, with choice, that's V. But no, it's an interesting problem whether, I have no idea whether the HOD conjecture implies the axiom of choice conjecture. It's a very interesting problem about ZF models, but it's certainly a possibility.
Questions? Okay, so let's take the speaker again. We continue in 15 minutes. We have a 15-minute break.
So